looking at Newton's second law, we're going to do example B in that section of the package, and we're going to look at the same 4-kilogram box from example A, but instead of the box just being pushed horizontally, it's being dragged by a woman using a rope that has an incline of 30 degrees. So in this case, if I'm going to draw the free body diagram, because that's something you should do with every actual situation you're given. So in this case, I've got my box. Okay, I know that the force of gravity is downwards like this, F, G, and I'm going to put my positive X in this direction and my positive Y going up. I know that my force of friction is going to prevent the forward motion. So we'll call that F. And I know that the pulling force that she is applying to this box is at a 30-degree angle. So here we've got our 30. All right, so I'm drawing this. I'm going to call it my tension force because it's a rope. And then we've got our normal force pointing straight up. So when you look at this kind of situation, you're also given a lot of other variables, and you should write these variables down on the side. So let's take some time to do that. So the question is asking us, it's saying using a rope with a 30-degree incline above the horizontal, a 4-kilogram object, which is initially at rest, is pulled over a horizontal surface with a force of 20 newtons. The friction force, or the force of friction, is equivalent to 12 newtons. First part of this question, they're asking what is the object's acceleration? The second question, what is the distance covered by the object in 2 seconds if it is initially at rest? And then we switch to dynamics and we say, what is the magnitude of the normal force? So parts A and B are looking at the kinematics of this, and part C is looking at the dynamics. Now, we cannot leave Ft as such because Ft does not abide by our X and Y axis. This is where we are going to calculate the actual X component of this, so that's Ftx, and we're going to calculate the Y component of this, is Fty. Okay, and so when we do our Y's and we do our X's, later on, we're going to have to remember to break down, like any normal vector, our Ft, because all of the other vectors are either in the horizontal or the vertical. So if we go with part A was asking for acceleration. What is the acceleration of this system? So in this case, the object is moving forward. Okay, it starts at rest and it picks up speed. Now, in this case, I'm only going to be dealing with the actual forces that are in the X. I don't care about my Fg or my Fn or my Fty, but I do care about my Ftx and my Fx, because my force of friction is only in the X. So in this case, according to Newton's second law, I know that my resultant force in the X is going to be equal to the sum of all of my X's. So Ftx plus Ff. I'm not going to mark Ffx because Ff is only in the X. And I know that according to Newton's second law, this is also equal to the mass of the object times the acceleration in the X. This is the variable I'm looking for. Okay? So if I write all this out again, I can rearrange this formula to solve for X, to isolate that AX. If we rewrite this, let's write this to actually talk about direction here. Although I've added them, in reality, this would imply that they're going in the same direction, and we know that they're not. If I want to rewrite this, I know that my Ftx is going in the positive direction, whereas my FF is going in the negative direction. And I know that this is going to be equal to the mass of the object times acceleration in the x. Now, if I want to isolate this guy, AX, I've got to divide both sides by m, which cancels it out here. So I'm left with AX being equal to, now here's where our vectors come in. Because FT as a whole cannot be added here, only the x component of the FT. I know this, so I'm going to sit here and go FT cos, my angle of elevation, which is 30 degrees, okay, 30 degrees, minus my F value, which is going to be divided by m. Input these numbers in, and you end up with an acceleration of 1.3 meters per second squared. Okay? Now, now that I have that acceleration, now that I have my AX, the second question is asking me to figure out the distance covered by the object in 2 seconds of time, if it's initially at rest. Well, in order to do that, I've simply got to use one of my 4 kinematic formulas, my equations. I believe that you could probably use x, okay, so this is for B. X final is going to be equal to x initial plus VIXT plus 1/2 AXT squared. I know that we're starting at 0, and I know that I'm starting at rest. So these two cancel out. I'm left with XF equal to 1/2 AXT squared. I input my data. That's 1/2 times 1.3 meters per second squared times 2 seconds squared, which ends up giving me a distance of 2.66 meters. So in 2 seconds, not only does this box accelerate at a rate of 1.3 meters per second squared, but it also moves a distance of 2.66 meters. Now, this would be all fine and good. These are my kinematic portions of these equations. Now what I'm going to do is I'm going to actually show you that the third part, okay, finding out the normal force here, has nothing to do with accelerations and times and distances. We go back to the forces that are on, that are exposed, or that a body exposed to a number of forces. So C is asking us for the normal force in the object. And if we remember, and we go up to our free body diagram at the top, we're basically looking for this guy. I know you want to say, oh, but it's opposite. Normal force is opposite the force of gravity. No, not in this case. In this case, how many forces in the X do we have? We've got our normal force. We've also got the Y component of our tension. And then in the negative, we've got Fg. If this object is not sinking into the ground, it's staying on the surface, the sum of these two must be equal to the sum of the negative. Let's see if that's actually the case. So if we look at this from the Y, we've got our Fn that we're looking for. If we write out the Newton's second law, states that forces, or the resultant force in the Y, is going to be equal to the sum of all the Y forces. So Ft Y plus Fn plus Fg, which will be equal to the mass of the object times acceleration in the Y. So here's my question. Is there acceleration in the Y? Is this box being dropped? Nope, it is not. So what do we know about acceleration in the Y? It's got none. So basically, these guys are in equilibrium with one another. because this is going to be multiplied here and to give you 0. When the sum of all your forces is 0, then you know that you're at equilibrium. Okay? So in this case, we're going to sit here and we're going to work this out. If we're looking for this guy to remain positive and we want to isolate the other two, let's have a look at this and say Fn is going to be equal to, okay, F negative Fg plus Fty. Okay? Correction. Correction. What are the positives? What are the negatives? Right now they're all positive, and that's not the case. I know that 0 is going to be equal to my two positives here, Fty plus Fn, because they're going upwards, minus Fg. So in order to figure all of this out, I've got to start substituting what I know. All right, so what I know is Fn. I know what Fn is going to be. It's going to be the positive of Fg. Fty breaks down to Ft sine 30 degrees, okay, plus Mg minus Fg. Now I'm isolating my Fn. So this guy over here needs to be brought over. Okay? We basically do what we had done above. We end up with Fn being equal to Mg. We subtract the actual Ft sine theta, because we're trying to isolate this guy, right? And that ends up breaking down to the positive 4 kg times 9.8 meters per second squared in kilograms meters per second squared. Okay, which will give you a number. Now all of this minus the breakdown of Fty, which is Ft sine theta, or 20 newtons sine 30 degrees. You end up with a final answer of 29 newtons. So in reality, the reason that this number, this normal force, is smaller than the actual force of gravity, because if you multiplied 9.8 kilogram meters per second squared times 4 kilograms, you would get something much higher than 29. What ends up happening here is if we go back to our actual diagram, okay, these two positives here, the Fty and Fn, are in the plus, according to my y-axis. These have to equal Fg. Okay, the sum of all of the x's must equal the sum of all of the sum of all of the positive y's must equal the sum of all the negative y's. So this is why your actual normal force down here is smaller than the force of gravity, because it's the sum of Fn plus Fty is going to be equal to Fg.